Hey, welcome to Gaffy's Grinds. In this video, we're going to be taking a look at the 2020 exam question and breaking it down. Question 6 on fuels and heats of reaction. And we're specifically focused not on the theory part, but on the calculation part. So this part here, down here, part D. And this type of calculation comes up every single year on the exam. So it's something that's very important that you master. It's usually worth somewhere between 18 to 21 marks. And they're pretty similar if you can master the skills. Now, there's two main ways of doing this. In my video series on fuels and heats of reaction, in the last video, if you look at that playlist, I've done it another way than what I'm going to do it here, because there are two main methods. The other way makes a lot of sense to me. In some ways, it uses an equation, but it can be a little bit easy to go wrong in. If you've watched that video and you like that method and it makes sense, then you can go ahead and use that if you can consistently get it right. I'm going to show you a different method today. This is the method that most teachers would teach. It uses a variety of simultaneous equations. Essentially, that's what you're talking about. They are chemical equations, but they're used in the same way you would solve simultaneous equations in maths, for example. And they're pretty straightforward or pretty easy. But there's some key skills you have to be able to do. Okay, if you open question 6 and read along with me, we're going to go ahead and ignore a lot of the stuff at the top because we're really only focused on this part down here, part D. Okay, so what I'm going to ask you to do now is I'm going to ask you to pause the video and read D part 2 from there to there. Okay, so you should only be playing if you've gone ahead and read this, and I do have it typed out again down here. Okay, and what we're going to do is we're going to break it down. We're going to break it down into the simplest steps that you have to do that you can follow along, and they should work for you for any of these types of questions. And the big idea here, remember, is Hess's law. What you learn in Hess's law is that the energy change in a reaction is the same whether it happens in one step or a variety of steps. So usually what they'll do here in these questions is they'll give you a variety of information that help you make up the individual steps of a reaction. And then you have to put them together to find the overall energy change. That's usually what we're going to do. All right, so the first skill you have to learn here is to be able to derive some equations from the information that they give you. And before we do that, the information is always given to you in the same way. They'll say the heats of formation, or they might say the heats of combustion, or they might say the heats of neutralization, but it's usually the heats of formation. And then they'll give you 2 or 3 names: propane, carbon dioxide, and water. So notice the way they give you the 3 names first, and then they'll give you the 3 numbers that correspond to those names: propane, carbon dioxide, and water, and then they give you 3 numbers in a row. Now, this can go wrong with students matching the wrong numbers with the wrong names. So the very first thing I do, I never use highlighters that much, but definitely in this question, it's helpful to use a highlighter. So I'm highlighting here propane and the first number, because the first number that comes goes with the first name. So in this case, minus 104.7 is the heat of formation of propane. Then using a different highlighter, I suggest you do this too. We've got carbon dioxide is the second chemical, and its heat of formation is minus 393.5. And then lastly, in a final color, we'll go with this this pink color. We have water, and it's the third number, minus 285.8 kilojoules per mole. Okay, and that's the way they always give it to you, and that can be the first place that catches students out. All right. So once you do that, you've actually gone a bit of the way to making sure you get this question right. It says, write a balanced equation for the combustion of propane in plentiful oxygen supply. So overall, the reaction we want to know about at the end is the combustion of propane in plentiful oxygen. So excess oxygen, loads of it. And use the data provided to calculate the heat of combustion of propane. All right, so that's the overall, the big picture. What we want to find at the end is the heat of combustion of propane. But before we worry about the heat of combustion of propane, let's deal with this up here. What equations do we need to form each of these substances? Now, remember what heat of formation means. Heat of formation means the heat change when 1 mole of a substance, that's these 3 substances, 1 mole of a compound is formed from its elements. Okay, so what we have to do is, as it says here, derive 3 equations that show the formation of each of these substances from their elements. So I'm going to go ahead and start doing the first one for you, propane. Okay, so what I want to do is I want to make propane. So I'm going to have an arrow here that forms propane. Okay, so what is propane? Meet, eat, prop. 3 carbons. Okay, so it's C3, and then it's an alkane, so it has the general formula CnH2n plus 2. You guys should know that. I have to assume you guys know some chemistry, otherwise you shouldn't really be doing these questions. So C3H8 is my compound, and I want to form it from its elements. So the elements are carbon plus, and this is one thing we must know, hydrogen is a diatomic element, H2. Carbon plus hydrogen. Now that's not balanced yet, so I need to balance it. So to balance this, I've got to put a 3 here. There's 3 carbons in propane, and then there are 8 hydrogens in propane, so I have to put a 4 here. Okay, so what it's telling me here is that when I form 1 mole, so heat of formation is always about 1 mole, and when I form 1 mole of it, the heat change is this here. So delta H for this is equal to minus 104.7 kilojoules. That's what it's telling me, okay? All right, so you've seen the way I've done that one. What I want you to do now is I want you to pause the video and do the next 2, the other 3 equations that we color-coded above. Pause the video and do that now. Okay, so what you should be doing is you should be doing CO2. So the second equation will form in CO2. By the way, you can number these if you like. This is number 1, just to keep them. So we're doing number 2 now. Not necessarily to get the marks right, but just to keep, if you like, to keep things organized. And of course, that's formed from carbon plus the element oxygen, which is a diatom. Okay, very important you know your diatoms. H2, O2, N2, H2, N2, O2, F2, Cl2, and I2. Okay, you have to know that. All right, so as you can see, this is already balanced, and we formed 1 mole of CO2, which is what we want. So that gives me delta H equals to where are we at? It's minus 393, minus 393.5 kilojoules per mole. Yeah, sorry, that should be kilojoules mole minus 1. Kilojoules mole minus 1. Okay, and then last of all, the third one should be we're forming water. H2O, and we want to form 1 mole of the water. So that means I need to take the elements H2 plus O2. Both of them are diatoms, and then we have to balance this and make sure that we leave this as a 1, because again, heat of formation is all about forming 1 mole of the product. So I have to balance everything according to that, or relative to that. The hydrogens are okay, but for the oxygens, I need a half. Okay, and you should have done this with me before. Okay, and if you're not in my class, you should have done it in the video. So you shouldn't be here if you haven't. If that doesn't make any sense to you, then you need to go back a little bit. Okay, equals minus 285.5 kilojoules, mole to minus 1. All right, and you're already getting some of the marks, guys, all right? Just for writing those equations, I think you're getting a lot of the marks. Let me check here. I actually think you might be getting, yeah, you're getting 9 marks for writing those 3 out there. That's how that works, all right? So you're getting rewarded for the work that you're putting in already. Okay, what do we have to do with it then? Generally, after you've written out your equations, you generally need to think about what you're looking for and manipulate the equations to suit. So first of all here, it says, what are we looking for? So back up here, it says to write a balanced equation or the heat of combustion, or so the combustion of propane in a plentiful oxygen supply. All right, so I'm going to write, what I'm going to do is I'm going to ask you to do that. Can you write an equation for the combustion of propane? Pause the video and write a balanced equation for the combustion of propane. Okay, so you should only be playing if you've tried to write the balanced equation. We start with propane, C3H8, and we add to it, we're going to burn it in oxygen. So we're adding O2. Now, this is another thing that you always have to know when you're talking about combustion equations, combustion reactions. They always have the same 2 products. So if you weren't sure and you didn't know how to start, could you finish this off for me now? What are the products whenever we combust a hydrocarbon? Pause the video and finish this off for me. Okay, so what you should have said is we have CO2 plus, sorry, I'm just going to make that plus a bit more spread out over here, plus H2O. Always carbon dioxide and water when we burn hydrocarbon. Now let's balance all of this. Now the one caveat I have is that you have to make sure this stays 1 mole, because heat of combustion, the definition, is the energy change when 1 mole of fuel, which is this, it has to stay 1, is burned in excess oxygen. So leave this as 1 and balance everything else according to that. Okay, so pause the video and balance this equation now, please. All right, so what we should be doing is we should be changing this to a 3 because there are 3 carbons over here, C3, and there's only 1 here. So we balance that first. I'm going to leave the O2s to last because this is a nice one to balance because it's by itself. So the next thing I'm going to do is going to go to the hydrogens. So there are 8 hydrogens here on the left. There are only 2 over here. So 4 times 2 gives me 8 hydrogens. So now it's left with the oxygens. I've got 3 times 2 oxygens, which is 6. And I've got 4 times 1 oxygen, which is 4. So 6 and 4 is 10. So to balance this is a 5 here. Okay, and what we want to find here is delta H is equal to a question mark. We want to know what that is there. Okay. Okay, so the last thing we're going to do here is it says by inspection of the equations, we try to figure out how to manipulate them to get what we are looking for. In other words, so we're going to number the equations and state clearly what manipulation has been carried out on each one, and if none, state so. Make sure that whatever you do to the equation, you also do to the delta H. That's a lot of kind of rubbish there, but we've got a space below to work in, and we're going to go ahead and we're going to work on that now. So I'm just going to rewrite my equation. Actually, do you know what? I'm going to rewrite my equations again. You might not have to do this. I'm going to number them, and I'm going to say, okay, so the first one was C plus H2. What was it? C plus H2. It's me. C3H8. That's to make C3H8. And that's 3 and 4. And that was a delta H equals to minus, was it? 104.7. Minus 104.7. Okay, and then we had number 2, which was we were forming CO2, and it was just C plus O2, and that was giving me a delta H equals to minus 393.5. And then number 3 was forming water, H2O, H2 plus a half O2, and that was giving me a delta H of minus 285.5. 285.5. Okay, so what we're doing is we are looking to compare the equations here with the equations up here. Okay, so we're trying to compare these 3 equations and manipulate them in some way to make this equation. Now, what can we do here? What we can do is we can reverse the equation, or we can multiply the whole equation by a number. Okay, it's basically what we're going to be doing. Now, what we're trying to highlight is what do we have in each equation that matches the one above. So straight away, I'm seeing that this equation here has this up here. That's what we're missing. Okay, so what I'm going to do to this equation is I am going to reverse it. Reverse. That's what I'm going to do to this equation. Do I need to multiply it by anything? I don't, because this is already 1 mole and I want 1 mole here. So I'm just going to reverse it. What else do I have? Here I see CO2. Actually, do you know what? Different color here, yellow. Here I see what's in common is I've got CO2. And up here, I've got CO2. And I'm only interested in the compounds, by the way, guys. Elements, not relevant, because elements don't have heat of formation. So as you can see here, there is O2 here and there's O2. So you're going, oh, why are you picking the CO2 and not the O2? Well, the reason for that is that oxygen elements don't have a heat of formation. Only compounds do. So that's what I'm going to do here. So what do I want to do? What's the difference between this one and this one? Well, this one up here is 3 times this. So what I'm going to do to this is I'm going to times it by 3. I don't need to reverse it because this is already in the products and it's already in the products up here. So why did I reverse this one in blue? I reversed this one in blue because it's in the products here and it's in the reactants here. Okay, now if I I will get to that reversing now. In the third equation, what do I see? In the third equation, I see water, H2O. Both of these are elements, so it's not relevant. So water here, and I see water here. So what's the difference? Well, they're on the right side. They're already in the products. but I have to times it by 4 to make it be like the main equation. Okay, so I'm going to rewrite this out now. Okay, I'm going to rewrite this out. I'm going to have, so I'm basically writing this in reverse. C3H8 arrow 3C plus 4H2s. And that's a delta H equals to, now whatever this was, we'll reverse the equation. So this is now the same number, but it's the opposite sign. So this would be now an endothermic reaction and be a positive number, 104.7 if I wanted to do that. So if I'm forming C3H8, it gives out heat, but if I was breaking it down into its elements again, it would take in heat. All right, so that's, hopefully you can see what I've done there, reverse the equation and change the sign. Okay, all right, on to the next one. This one doesn't get reversed, so it's still C plus O2, and these are reacting to make CO2, but now it's times by 3. So now it's 3C plus 3 O2s react to make 3 CO2s. Okay, and that gives me a delta H equals to, well, what I want to know is what's minus 393.5. So 393.5 equals times by 3. So 1180.5. So minus 1180.5. Okay, and then last of all, this one here is leave it the way it is. H2 plus half O2 reacts to make H2O. So it's still in the same order. I haven't reversed it, but I got times it by 4. So this becomes 4. This becomes half times 4, which is 2, and this becomes 4 H2Os. Delta H equals to, so now I need that number times 4. So it's minus 285.5 times by 4. 1142, so minus 1142. Okay, so now what we can do is we can look at the equations, okay, and we can basically add them up, find what's common, find what's not common, and obviously anything that that can cancel, you can cancel, or anything that divides equally to give us 0, we can cancel out. So watch this, all right? I've got 3 carbons in the product here, and I've got 3 carbons in the reactants here. So those have balanced each other out. I can remove them from the equation. I've got 4 hydrogens here, 4 H2s in the products here, and I've got 4 H2s in the reactants here. So these can cancel out to remove each other if I like. I don't see anything else that can cancel out. So what equation am I left with? Well, I'm left with this here. C3H8 is a reactant. So C3H8. Okay. I see 3 O2s and 2 more O2s. So hopefully you can see that with this highlighter, I'm highlighting all the oxygens I have. O2s and O2s, which gives me a total of 5 O2s plus 5 O2s. Then I have the 3 arrows. So I have no more reactants here, and I can form the products. What do I have here? I have 3 CO2s, as you can see here as a product. 3 CO2s plus I have 4 H2Os. Plus 4 H2Os. Watch how I can go back to my original equation and check, is that what I was supposed to find? Checking your original equation up here. And it is C3H8, 5 O2s, 3 CO2s plus 4 H2O. So you know you've done it bang on. You know you've got it right. And just the way you kind of added up those 3 equations, you added up these 3 equations to make the main equation, you're going to add up the delta H's. So you've got plus 104.7 minus 1180.5 minus 1142. So what I want you guys to do now is I want you to pause the video and calculate what is the overall delta H, the overall energy change for this reaction. Pause the video and do that now. Okay, so the overall energy change for this reaction you should have got was minus 2219.0 kilojoules per mole. That's what you should have got. Okay, and what that tells us is that it doesn't matter if we do it in these 3 steps or just in this one step, the total value will be the same. Okay, and that's what Hess's law says. All right, so that's how you do that question, 2020 question, sorry, the 2020 question on heats of reaction. In the follow-up questions, I'm going to go a little bit quicker than this. I'm not going to be showing you just as much how to do it. So this is a good starting place for learning how to do these calculations. Let me know in the comments, do you prefer this method or do you prefer the original equation method that I gave you with the graph and stuff, where we did the energy of the heat of formation, take away the heat of formation of the products, take away heat of formation of the reactants. Let me know which ones you preferred. A lot of students prefer this way, but it's good to see both ways. Let me know what you think, and I'll see you in the next one.